Hello students, in this video we will discuss about the application of Ampere's Circuital Law, and we will calculate magnetic field inside a long straight solenoid. What is solenoid? You all know that if you bend a wire in this form, you can say that if you bend a wire in a spring form or in a helix form, then this become a solenoid. This is the solenoid. If the current is moving in the coils, you all know that if the current is moving in this direction, this is the coil, and this is the direction of current, and we have to calculate magnetic field at the center. You know that magnetic field by the right hand rule will be into the plane. Magnetic field is inside. Okay, let us suppose this coil is this, like that. Okay, you will see that if the current is in this direction, magnetic field will be in this side. Okay, second coil, magnetic field will be inside at the center. One coil, first coil, have the direction at the center. Direction of magnetic field at the center is in this direction, and in the second coil the direction of movement of the current is the same. That's why at the second coil magnetic field is also in the same direction. Like their third, fourth, fifth, means all the coils will have the magnetic field in the same direction. That means the magnetic field is in this direction. Magnetic field inside the solenoid is in this direction, and in simple way you can say that magnetic field is like that. Magnetic field inside the solenoid is like that. Okay, like that means magnetic field inside the solenoid is strong and outside is very weak, or you can say that magnetic field outside is negligible or absent. And in this video we have to calculate magnetic field inside a long straight solenoid. Let us suppose this is the coil. Wire is wounded like that. This is the coil, and cut it from the middle. What structure you will have? You will have a structure like that. One wire was wounded in this direction, as like that. But if you cut from the middle, you will have one wire present, half circle present, half circle absent, half circle present, half circle absent. Take only half portion. Inside portion take, outside portion just remove it from there. You will have only half of the wire. What you will see, the structure will be like that. This is the upper wire and this is the lower wire. Okay, means current is going in the wire and return from that wire. Means current is rotating like that. Okay, I hope you are getting. This is the direction of current, not magnetic field. This symbol is also used for magnetic field, but here this symbol shows the direction of the current. And and we have to calculate magnetic field at the center or inside the solenoid. Just because this is the application of Ampere circuital law, apply the Ampere circuital law. You may have any shape of the Ampere circuit. It may be rectangular, it may be circular, it may be any other shape, but it should be, we can say that it must be a closed circuit. Let us suppose this is the circuit. This dot line shows that this is the very large, and we can say that this present at the infinite. This wire present at the infinite. This is A, this is B. The length of this wire is a small l, and this point is C, this point is small d. You will see that this is the capital L, and capital N is the what? Capital N is the total number of turns. Total number of turns. How many turns is there in the solenoid? Okay. And you know that small n is equals to capital N upon capital L. What is this? This is the total number per unit length. Total number of turns per unit length. Small n is the total number of turns per unit length. Okay, means 1 meter wire will have small n number of turns. 1 meter wire will have a small n number of turns. 2 meter of wire will have 2n number of turns, and 3 meter will have 3n number of turns. Similarly, L into N will have number of turns in the length is small l. Number of turns in this means you can say that this number, only this number is small n into l. Small n l is the number of turns present in the L length of the solenoid. Okay, let us apply Ampere's circuital law. Ampere's circuital law is magnetic field, line integral of magnetic field is equals to mu naught times net current. Not only current but net current. This is not a circle. This is a rectangle. Then this portion you can break like that. Line integral of magnetic field from A to B, B to C, C to D, D to A to B, DL, A to B, DL. What is the direction of magnetic field? Let us suppose current is in this direction, that means magnetic field will be in this direction. It may be, if you reverse the current, then magnetic field will be in this direction. Let us suppose the magnetic field is in this direction. The length L, this is the L. Length is in this same direction, means DL element have the direction that, and magnetic field in the same direction. That's why we have taken BDL cos 0 plus B2C BDL into B2C. The DL direction, DL element have direction this, and magnetic field is this. This means this is 90 degree. Cos 90 degree plus integral C to D, C to D B DL cos 0 plus D to A in this direction, magnetic field is this direction, angle is 90 degree. BDL cos 90 is equals to mu naught times net current. Okay, let us talk about these 4 terms. This is 90 degree, 0. This is also 90 degree, 0. Cos 90 is 0. This portion is 0. This portion is 0. What about this portion? This portion B, because this DC is at a very long distance. That means magnetic field due to this solenoid is absent. You can say that B is equals to 0. If this B is equals to 0, that means whole term is equals to 0. These three terms is equals to 0. Only this terms remains. This is what? A to B. B is constant. You can take out of your integral. dl A to B cos 0 is 1. That is equals to mu naught times net current. What is net current? Net current is what? If only one wire is passing through that area, only one. If only one wire is present, then the net current will be I. But only one wire is not crossing that area. There may be a number of wires. How many numbers? This much. L into N. Okay? L into L number of wires threading this particular area. Okay? Then this is the number of wire. One wire have current I, two wire will have 2I, 5 wire current, 5 wire will have net current 5I. NL number of wires will have NLI, this much current. This is the net current. Okay, and you know that integral dl from A to B, this is equals to a small l. You can write in place of integration dl A to B, that is L, in place of in NLI and LL cancel out. Finally you can write B is equals to mu naught NI. Okay, I hope you understood this video, and this is the result. B is equals to mu naught times N into I, where small n is the total number of turns per unit length. Okay, total number of the turns in the solenoid and total length of the solenoid. This is the small n. I hope you understood this video, and thanks for watching.